Hi everyone, this lecture is about PWM, pulse width modulation. I tried to record our lecture. Unfortunately, my tablet went out of space and then it just cut it. So I'm recording one more time here. So today we'll talk about PWM. And PWM is a great way to generate an analog-like signal using digital output by toggling it between high and low states. Okay, so this was a sentence. What does it mean? It means that imagine we have a signal here, okay? We have a signal here, and then for some time, let's call this the pulse width. We keep it on, and then after that, we turn it off, and then we keep it off. So in a way, it's just like, blinking an LED, but we set the pin high, and then we keep it there by introducing some amount of delay, let's say T1, and then after that we set the pin low, and then we keep it low for that amount of time. For another amount of time, let's say T2. By doing this, we have, as we said, we introduce a signal that is for T1 time of the period is on, and then for T2 amount of time it's off. And then we repeat the same thing in, let's say, a while loop. So we keep repeating this. So the period of this pulse that is going to be generated is going to be T1 plus T2. The amount of time that this signal is on compared to the total amount of time that things get repeated is called duty cycle. So duty cycle is basically T1 over T1 plus T2. Or in a way, you can say it's pulse width over the period. Now, you might be asking, well, actually, just here, you're showing me a signal that 50% of the time it's on and 50% of the time it's off. Isn't that like toggling an LED? And if that, I've done that. It doesn't look like analog. It looks like T1% of the time it's on, and 50% of the time it's off. Yes, that's absolutely fine. If our T1 and T2, let's say we're 1 second, then this signal wouldn't look like an analog signal, analog voltage. In fact, it looks like T1 time, it looks like 0 volt, and T2 time, the T1 time looks like 3.3 volt going through, and T2 time, it looks like 0 volt. This is completely digital. But what if instead of this, we had T1 to be 1 millisecond and T2 being 1 millisecond too? In that case, when you're toggling, it's not going to look like output. The output is not going to look like 3.3 sometimes and 0 sometimes. No, it would look like an average value. It will look like V average or V output will look like V average, which is 50% of our Vref, or VDD, let's say, or VDD, which is going to be 1.65 volt. So if we do this toggling fast enough, meaning that frequency matters, fast enough, then we would get a voltage that looks like an analog voltage that is equal to duty cycle multiplied by VDD as the output. So frequency matters. Frequency, or being fast enough, is the key in making the PWM looking like an analog-like signal. If it was slow, it wouldn't have worked. So that's the second parameter that we talked about here. The third parameter is the resolution. The resolution is, so with the toggling, if you do it even 50% of the time, even fast enough, the levels you would get is you would get V out to be 1.6.5 volt, let's say, right? You can't achieve every level, but because we can implement PWMs by timers, then we achieve something much higher. We achieve a resolution that is even higher than the resolution of a DAC with the timers period, basically, and we will explain this. So that's the resolution is what makes the PWM signal a smooth analog one. Otherwise, if the resolution was low and let's say we only had certain steps like 0 volt, 1 volt, 2 volt going to the output, then the output looks like, imagine a robot. It will look like boom, 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 like it will look like a certain positions, like here, 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 not like an arm that moves very slowly from here to here. You see, this is the difference. Resolution causes, low resolution, yes, might give you like different stages of voltage, but it doesn't give you that smooth rotation. So you might ask, well, if I have DAC, DAC is delivering the true analog value, then why would I need PWM, which is kind of like a pseudo analog or analog-like? In fact, it's not analog. It's a digital output that sometimes it's off, sometimes it's on as push-pull, and then it looks like an analog. It's actually an average voltage. Why should I rely on this one? The reason is, first of all, in your STM32, the DAC you have is 12 bit, sorry. And that gives you resolution of 2 to the power 12, let's say. But PWM, thanks to the timers and the fact that we have some timers with 16-bit or 32-bit periods, it can give you 16 more times even resolution as the minimum. So you would have 2 to the power of 16 or 2 to the power of 32. Going from 0 to these values, basically. 0 to 2 to the power of 16 minus 1. Or 0 to 2 to the power of 32 minus 1. Instead of 0 to 2 to the power of 12 minus 1. So that's another thing. Another important part, which is the most important one, is that a DAC output is usually microamps. It can't drive loads like an LED or a motor or a speaker. It can't do those things. It can't drive loads. But PWM can. It can provide current to a load and drive it, and in fact helps us get that smooth brightness or a smooth change in position of a robot by controlling the duty cycle. Okay, so that's another point to remember about DAC versus PWM. The other thing is that since PWM is actually a digital output, not a analog one, it's more immune. PWM is more immune to noise, because you know that it should be 0 or 1. It can't be any value, as opposed to if you have a slight difference in the analog output of a DAC, then the output voltage can change. Immune to noise because it's digital. Its output is digital. So that's another important part. Okay, now let's see how we are achieving PWM using timers. So we have the CPU clock coming in, or APB clock coming in, and then just like a regular timer, what we are doing is we are dividing that by prescaler value, register prescaler plus 1. So let's say we have 84 megahertz coming in. Then we have our prescaler, so our frequency is going to be 84 megahertz over prescaler plus 1. Then we give this to something that acts like a counter, right? This counter is going to go from 0 to the period of that frequency, let's say, right? But this period is defined by a register called auto reload. This auto reload, what does it do? Auto reloads defines the period, as we said, and in fact it says you have to go from 0 to ARR before you reset to 0. Okay, so this, in fact, we'll talk about it, that it defines our resolution, the resolution of duty cycle, or the resolution, if it defines the resolution of the duty cycle, it defines the resolution of the output voltage. So prescaler defines the frequency of our PWM. ARR defines the resolution of PWM. Then another register we have is compare, CCR. This defines the duty cycle, because compare says if the counter is below the compare value, then the signal should be up. The signal should be high. If it's the counter goes after the compare value, then the signal goes low. So here, if I want to draw this, it would be like, let's say the timer starts from 0 and it goes to ARR before it goes back, right? So, and here we have 1, 2, 3, and in the middle here I have my compare value, the CCR. This is CCR, and then let's say this is ARR minus 1. So the signal is 1 before the CCR and then 0 after the CCR. ARR defines the period of our signal. CCR helps us define the duty cycle. So that's almost like the pulse width. The CCR defines the width. And the duty cycle is CCR over 1 plus ARR. Okay, and then based on the counter compared to the compare value, we get our PWM output. Let's see this in practice. So we have the APB clock over the prescaler, as we talked about. Okay, and we would get the timer clock as this value. For example, if we had a 84 megahertz timer on the APB and the prescaler is 83, then the timer clock is going to be 84 megahertz over 84, which is going to be 1 megahertz. Then for if ARR is 999, then the PWM frequency is going to be 1 megahertz over 1000, which is going to be 1 kilohertz. And we know that the period of this PWM period is 1 over PWM frequency, or it's defined by in time basically. It's going to be 1 over 1 kilohertz, which is 1 millisecond. That's our PWM. Now it says if the CCR is 500, what is the duty cycle? In this case, duty cycle is defined with, this is ARR plus 1. So it's going to be 500 over 1000. It's going to be 50%. And we can see this here, like 1/100th of it here. If our ARR is 9, and then the compare value is 5, set as here. This is our compare value, CCR is here. So it says if the counter is less than the CCR, we get high voltage. If it is more than that, we get low voltage. That's why we get this. That is going to be our output based on time. Now, there are a couple of important points in this slide. Let's look at these in more details. So we said, okay, so the duty cycle is CCR over 1 plus ARR. Okay? And then we know that the V output is V average of our signal, which is going to be the duty cycle multiplied by VDD. So in the case that ARR was 9, right? And then our CCR was 5, the duty cycle was 50%, and the V out would be, let's say, 1.65 volt. And let's say VDD is 3.3 volt. Now, if I change the CCR to 4, then I would get a duty cycle of 40%, and V output would be about 1.32 volt. Now the question is, would I be able to achieve something in the middle here, would I be able to get a duty cycle of 45% or a V output of 1.78 volt? Is this possible? Since ARR is usually fixed, well, it's fixed, not usually, it's fixed, and it is dictated based on the frequency of the PWM signal. Then in order to change the V out, the only thing we have is our duty cycle, which in the duty cycle, the only thing we have that can be changed is CCR. Okay? And CCR, we know that only, it's a counter basically. So it can go only up by one step. So in fact, this shows that if ARR is 9, in order to get to 45%, I would need a CCR of 4.5, which is not possible because the counter cannot be 4.5. So this shows that for ARR of 9, if ARR is 9, then the duty cycle steps or quantization or levels, they can be 1 over 1 plus 9, 10%. So the duty cycle can go from 0 to 10% to 20% to 30%. And that means that the V out levels can be 0, 0.33 volt, 0.65 volt, until the end, till we get to 3.3. So if we want a finer level of analog voltage, as we said, because that's important, that gives us the smooth change that we want, we need to change ARR. So ARR controls the resolution of the output. But ARR, we said it's fixed by the frequency. So this becomes an engineering problem, that if ARR is set high, then frequency is low, but resolution is high. So you have finer steps, finer levels of voltage. If ARR is low, frequency is higher, resolution is the one that is lower. So this is the trade-off. Again, so you should be mindful of these trade-offs. Okay, so we talked about the 3 registers that we have, and we talked about the duty cycle steps. Now here, GPIO, well, PWM is an output that we get on GPIO using a timer peripheral, basically. But the output that allows us to get PWM exactly is it's through alternate function. So that, like, it's not regular push-pull, but it's in fact converting it to PWM. And that means there are some specific GPIO pins that have that PWM capability. Not all of the pins have that, so you have to be mindful. Then we talked about something, the code implementation here. For the code implementation, what we are doing is we are setting 3 timers. We are setting 3 registers for the timer. Prescalers ARR that defines our frequency and resolution, defines the period of our signal, and then we set compare register, which defines the duty cycle. And so these are the 3 registers we need, and you can of course set this in the HAL library, again using a more intuitive notation. Here we have prescaler, period, which is again ARR, and then we have pulse widths. This pulse is basically pulse widths. Again, it shows our duty cycle, or it is basically our compare register. So for lab 1, you would be feeding what you call with ADC as the duty cycle to this PWM output. So some other important parts that we talked about is the different applications of PWM. We said, okay, it works for motor rotation, motor positioning, robot positioning. It works for LED dimming. It works for audio generation. But we talked about something from the beginning, that what made the PWM work. Now we are going to get into more details. So we said if we had a signal that would go on and off every second, then we would see it as on and off on the LED. But if that was happening every, let's say, 1 millisecond off, 1 millisecond on, which I'm showing you in reverse here, then we would see it as, let's say, 50% brightness. Okay. The reason for that is that the frequency of the PWM has to be faster than some environmental or mechanical sensors that we are talking about. For example, for our eye can understand changes within 60 Hertz or 70 Hertz bounds. If something happens faster than that, if frequency is faster than 60 to 70 Hertz, then our eye doesn't understand it, and it would instead averages it. And that's why PWM works in changing the brightness of an LED, because whatever is happening, that toggling, that the square wave that is being generated, it's happening within a period that is much higher than the frequency of our eye. Like we said, like 1 kilohertz, or even if it is like 1 hertz, still our eye would average it. Or a servo motor that goes from 0, let's say, to 45, and then 90 degrees. The mechanical inertia that we have in these motors, it would basically slow things down for us, or let's say it wouldn't be able to, it would average for us. That's a better term. Again, it would average it. So if you make a change to the speed, and turn the motor on and off fast enough, then the inertia would help into averaging that as a lower speed or a higher speed than a higher speed, basically. Or the audio generation here, the same thing. It's the natural frequency for our ear detection that can actually understand some changes or basically averages changes in the output of on and off. So in lab 1, what you're doing is that you are introducing or using a potentiometer as a knob to change the resistor value, and then that changing the resistor value is going to be changing the duty cycle of or is going to be input as the duty cycle of a PWM signal. It would be read as a DC, and then actually it's here that would become the duty cycle. You can convert it to something like a duty cycle and then feed it to an LED. So that's what you're doing. You're going from a changing resistor value, or as we said, potentiometer, to ADC, and then to the PWM generation, and then you're controlling the LED brightness. Here in the video that you saw in the class, we are using the potentiometer, and then we are controlling the speed of this fan. It can be the potentiometer, it can be a temperature sensor that you have in your smart home system that controls the temperature of your room and makes sure that it is within the bound that you want. And this is it for PWM. If you have more questions, feel free to ask them after the lectures or during my office hours. Thank you.